Can say now, good morning. Can say now that an alternative title for the talk is what system D gets wrong, but the organizers wouldn't allow me to run with it. Please, if you're not using Unix in your everyday work, raise your hand. That's what I expected. Also now raise your hand if you are familiar with Unix's principles and philosophy. Okay, I see some hands here, so we have some starting ground. Unix and Linux are powering modern information technology from Android, 1 billion shipments probably this year, technology stacks of the big companies, all of the world's top 500 supercomputers. How did it come to this? Unix was born at the famous AT&T Bell Labs, which was an amazing place. It was a place where they had 8 Nobel Prizes, 3 Turing Awards, the equivalent of a Nobel Prize in computer science, the place where radio astronomy was invented and cosmic radiation was discovered. They developed the first transatlantic phone cables. They invented the transistor, the CCD, the charge coupled device that powers our phone's cameras. They developed the theory of communication, which is behind error correction codes that we use in our systems and compression, lasers, fiber optics, radio satellites, TDMA and CDMA multiplexing, the basis of cellular networks, the C, C++, and awk programming languages, and of course, Unix. Inauspiciously, Unix started its life from a failure. In the 1960s and other projects, the Multics OS was going underway. And this was too ambitious for the hardware available at the time. It had some very interesting ideas, but it wasn't moving forward. It was a collaborative effort between MIT, AT&T Bell Labs, and General Electric. At some point, Bell Labs decided it was not going to succeed, and therefore it pulled out, was drowned in a tar pit of complexity. With their toy taken away from them, Ken Thompson, Dennis Ritchie, Doug McIlroy, and Joe Osana went off and developed an unnamed system on a PDP-7 computer, such as the one you see here. Based on those ideas, they created a funding proposal to buy a PDP-11 computer, a more powerful one, in order to create what one would describe today as a word processing facility. Over the years, the Unix patriarchs, we see Ken Thompson and Dennis Ritchie here, assembled around them a team of talented researchers to create a system that has profoundly shaped modern IT. This development continued. It later grew in the 1980s through work done at the University of California Computer Science Research Group by Bill Joy on a 32-bit VAX mini computers. And further development happened through this century's modern open communities. The history I'm going to describe is based on 3 main data sources. First of all, a repository on GitHub recording an important part of the Unix history as synthetic, for the most part, commits. So Git was not available in the 70s, 80s, even 90s, but I've synthesized those commits. The early versions were made possible thanks to Caldera, who at the point of time had the copyright of Unix, which released it with something that looks like an open source license. Early versions have not survived in machine-readable form, so particularly one version was only available as a printed memorandum, as an appendix to this memorandum. A group of volunteers scanned it, entered it, and amazingly made it run on a PDP emulator, and it could actually run, boot, and issue the login prompt and run commands. We're going to follow a path to discuss the history of the one you see, the orange path you see here, because it follows the work done at Bell Labs, then at Berkeley, then FreeBSD, because amazingly, this established a continuous half-century of code evolution. You can actually follow the code from one version to another, and of course, the ideas. Early versions are committed on the GitHub repository as snapshots, time-stamped with the time of change of each file. Later versions are imported from various version control systems, starting with RCS, CCS, Subversion, and then Git. Here are various parts of code as they survive from one generation to the next. And you see that starting from the 7th edition onwards, little parts continue to live from one generation to the next, to the Berkeley 4.3 and network editions, to 386 BSD, and then the FreeBSD versions. Sometimes I get asked what code can be found with git blame. There are indeed run git blame on various files. This is the oldest instance I have found in FreeBSD, modern FreeBSD code. There is still code committed in 1979 by Dennis Ritchie. A second data source I established was by typesetting the 3rd and 4th edition manuals and using the rest of the manuals as I found them available from their original nroff and troff sources. And incredibly, the 1970s shell scripts could run today with GNU groff. Finally, as a third data source, I created another GitHub repo containing the evolution of documented Unix facilities. So for each section of the Unix manual page, I created a table where you can look at at which release that particular facility became available. Based on those facilities, more than 500 architectural design decisions reflected by those facilities. My co-author of this work, Paris Avgeriou from the University of Groningen, and I created a list and went through them to establish the ones that we found most interesting, profound, noteworthy, and they are the ones we are going to discuss today to see what we can learn from the architecture evolution and establish a theory to describe it. So what lessons can we learn from the Unix architecture evolution? This is what I'm going to present today. First lesson number 1, write small programs. We often forget this. We work with large programs that have an accretion of features, but this need not be the case. Let's go back to the unnamed Unix that was developed on the PDP-7 computer. Amazingly, its kernel was less than 2,600 lines in assembly language. As Stephen Johnson has quipped, I once heard an old-timer growl at a young programmer, "I've written bootloaders that were shorter than your variable names." Second lesson, even from that primitive code, build modular code through partitioning, composition, layering. Let me give you an example here at how they did it in this very primitive system. We have various programs, you see them here, .s is for assembly code, and you see how some parts are partitioned, the editor, ed1 and .c by their names, the parts, and the system kernel S1 to S9.s. They form partitions that were distinct. Incidentally, ed forms the colon commands that we still use in VI. There was also layering there. The commands could call the kernel. The kernel did not have to know anything about commands. Again, nowadays we often see layering violations. A second lesson, again in that very underpowered hardware, is to value developer time over machine time. So use proper abstractions that help us as developers, as SREs, when we build the control plane for the systems that we manage, rather than trying to squeeze each millisecond or at a time, microsecond or nanosecond today of performance. Let me give you some examples here. That very primitive system already separated file metadata from file naming. You see the definition of the famous inode here on the left, and the internal kernel function that's still used today, nami, that converts names to inode identifiers. They were established at a time, and they are what allows us to delete files even when they are open or rename them while they are open, something that incredibly Microsoft Windows still doesn't get right. Another idea, devices as files. So all devices were not special things that had APIs to access. It would be easier to create an API for each device. All were discovered all were made available through the same process and the same idea, a file name in the file system. They created a file I/O API with system calls that we still use today, a small abstraction that will be used for everything. This is the power of well-chosen abstractions. At the time, you could see very baroque interfaces where you had to specify whether a file would be available and open for sequential or random access, if it would be text-based or binary file, if it would have some indexing, and so on. This very simple interface was well chosen, and this is why it survives today. Also a file system API, notice no directories at the time, but still the bare minimum of what we need. And amazingly, even an interpreter, at least two system commands, int for indentation and lcase to convert lowercase to uppercase, were written in a relatively high-level language called B, and this was implemented as a threaded code interpreter. Another lesson, prototype software before polishing it. So let's move to the first research edition developed on a PDP 1120 computer, the console of which you see here. This is the architecture of it as I tried to put it down. You see the commands, the user commands on the left, top left, the administrator commands on the top right. Beneath it, a layer of library functions. Underneath, in pink, the system call interface, and beneath it again, the kernel. A number of system calls were developed as I showed you. Here are the ones numbered on the left. In the middle, you see the same system calls in a modern FreeBSD edition. You see the same names, same numbers, and even on Linux, which doesn't share any source code with this system developed at the time, has the same system call names and even numbers. Another key idea is make each program do one thing and do it well. Already at the time, the system came with 50 commands, the ones you see here in the first section of the manual, and most of them commands were very simple, did just one thing. To give you an example, here on the left you see the manual page of the cat command. It just concatenates files and outputs them on the standard output. Contrast this with the cat command on Linux, which has more than 12 command line options. Try to think here what other commands could be better used in place of cat instead of adding options to cat. Also think how we could better implement the -- version and -- help options rather than adding them individually in each program. Another idea from the first research edition Unix is to avoid captive interfaces. What do I mean by that? Let's look at an example. Here's a documentation of the password file. You see that the fourth field is the program to use as a shell. So the shell was a normal user program, not something godlike given by the operating system gods, as was the case at the time for DEC or IBM operating systems, but something that could be configured in a file, and anyone could write a shell that they could use instead of the one provided by default. This has led to a lot of innovation in the area of shells. Many of the shells we use today were initially created in this way, and this can be used in various roles. I will give further examples later on. Another idea here is to write extensible programs and protocols. As an example, the programs could have their input and output redirected to files using the convention that's supported by the kernel and provided by the shell through the less than and greater than characters. And this became instrumental a bit later, as we shall see. Along the same lines, another way to allow additions was through user-contributed tools and games. You see various programs here that were contributed by users, not by the original team, including some games, the calendar, a sort utility, tic-tac-toe, and so on. Can you guess where these programs lived? In which directory? /USR for user contributed. Why are they documented? You see here their manual pages, because the developers created a small cron job that could periodically scan the files in user bin, and if there was no corresponding manual page, they would delete them. Last year, following this idea of extensibility, having an interface open to extensions, we can do things that we cannot dream about before. So I used a dynamic loader functionality to write a library that extends any command line interface, any program that uses the readline library, with a natural language for an AI interface. Let me give you a short demo here. So I have my shell prompt, and I type list C and header files.
I press escape V and I get immediately from OpenAI's API, ls_star.c star.h. Which is the largest one of them? Again, I press the magic escape character, and it gives me this pipeline. I can then issue another command. I can go into SQLite, which also has a command line interface with a read line, and ask what tables does the database contain. I can never remember the command between PostgreSQL and SQLite and MySQL, and it gives me this command. I'm using it on my browser's history. So now I say, show me the schema of the most places table. It's .schema. It gives me the schema of the table. And now I ask which is the ID of the most places row with the highest visitor count. So what do I most visit? I hope it's nothing embarrassing. It gives me this, just gives me the count from SQLite. This is, I just issue a command. Commands are given as context here. So now if I type, because I also have trouble remembering Git commands, show me the repo's remote location. It says it's git remote -v command. Excellent. Pour me a cup of coffee. Let's see this. Okay, you can't have everything. Another lesson, write programs that work together as filters that process text streams. This came about in the third research edition, 1973. We moved from 1970, but it put into power an idea first articulated by Doug McIlroy in 1964, when in a memo, he wrote that we need to have a facility that can connect programs as garden hoses together so that one can process the output of the other. This brought about the pipe system call, which you see documented here in assembly, its assembly language interface. The excitement at the time was so high that when the pipes became available, the people at Bell Labs pulled an all-nighter to allow the programs that at the time were using file names as input to be able to read from the standard input so that they could be converted in filters. So overnight, tens of programs were converted into filters. As Doug McIlroy commented, the energy of youth. Another key idea is to write maintainable programs. Again, I've seen very popular open source software has completely unreadable code, and of course, the opposite. This particularly good example here is the fourth research edition, which brought structured programming. They moved from assembly language to another language called NewB. I leave you to guess what the name of the NewB language came to be. So the kernel was, at the time, contained 6,300 lines of NewB and just 700 lines of PDP-11 assembly. Compare that to several editions earlier, the first editions, which had 250 global symbols and against just 105 functions and just 50 symbols in the fourth edition. So they eliminated a lot of publicly listed symbols. Along the same lines, the system also offered a language-independent API. See here, again, the documentation for the pipe system call, documented both in assembly language, with the registers where you get the results of the file descriptors, and as a C interface, where you see the two file descriptors provided in an array. The same system also offered data structure and redefinition and reuse. At the time, often data structures were individually defined by copy-pasting the struct from one file to another. So they decided, let's create header files where we can share those definitions and reuse them among multiple places. And you see here header files establishing key data structures of Unix. It's used, I counted, in more than 145 instances, and this allowed the evolution of data structures and the promotion of portability. Some data structures survive today in very different form, but they have survived thanks to the header files, which allowed them to be modified, and the programs would transparently continue using them. Another idea is to avoid unnecessary output. Today we see many programs that have headers and banners and copyright messages. All this is problematic because it makes it difficult to process that output unless there is special code to avoid outputting them if the output is not in a terminal, and also make the failures easy to diagnose. Appropriately for SREcon, this example I will describe is a 50-year-old incident. It involves this machine. It's a washing machine-sized thingy. That's a photo typesetter. What it did is it used this rotating drum you see on the right. It had images of characters. Magnifying glasses could be moved closer and farther to change the font size. This rotating drum could project letters to be developed, such as those in this plate, to be projected onto photographic film. Bell Labs acquired this photo typesetter. It got fed with paper tape, but of course Ken Thompson couldn't stand for that. So what he did was remove at the point where the tape reader was fed into the machine, he connected it serially to the PDP-11 and wrote a write-only device driver because it wasn't configured as a computer device, where people could send commands in order to phototypeset documents. So what happened at the particular, as Stephen Johnson described it, the way you used it is you took a piece of paper that was developed from the phototypesetter and you put it in an icky machine with chemicals and smells in order to develop it, and after several minutes to get the phototypeset output. One afternoon, several had the same experience. They typeset something, and after this long and smelly process, they get as output cannot open file foobar. They were so angry that they invented the standard error stream, and nowadays we know and we should follow the principle of outputting errors not on standard error, but on standard output, but on standard error. And of course, as SREs, we know also to properly log them. Another interesting idea is to use shell scripts to increase leverage and portability. I believe that shell scripts should be our first stop, but of course, not the only one. When we want to implement something, further stops can include scripting languages, high-level languages, and even more performant languages if nothing else works. So in the 5th edition, we see one example of a shell script, one that compiles command files. Another very deep lesson is to choose appropriately powerful abstractions. This came about, I found a good example of this in the 6th research edition. Here you see one of the most widely illegally photocopied documents, the notes that were created in New South Wales University by John Lyons with a complete source code of the kernel with annotations of it. As part of the 6th edition Unix, a portable C library was created as a replacement for the library that was previously available in assembly language. They had found that C was perfectly useful for writing library functions, and many of the ones you see here still survive until today. This allowed several of the programs painfully to be moved even to other operating systems just by porting the library. The idea of software tools came about through this library and this porting from the programs to various operating systems. An even better example of this idea came with the 7th edition Unix, a key edition. I will describe more lessons that we learned from it, that many have described an improvement not only from its predecessors, but also on its successors. So on the 7th edition, we had an event, a fateful discussion between Steve Johnson and Dennis Ritchie, where he said that I think it may be easier to port Unix to a new piece of hardware than to port a complex application, such as the tools I described before, from Unix to a new operating system. Nowadays, we see it all over the place. You can use Linux on machines ranging from our mobile phones to a $10 Raspberry Pi Zero to a many multi-million-dollar supercomputer. Another key idea from the 7th edition Unix is to separate mechanisms from policy. So the way something is provided as an interface from the way this API works underneath. Let me give you some examples. The 7th edition offered dynamic memory allocation and the standard I/O library, and it was a huge success. 26 programs, the ones you see here, immediately started using malloc for their allocation in place of ad hoc mechanisms and fixed allocations they had before. Static analysis. The lint program was developed came with the 7th edition, and this allowed programs to be checked for things that were not compile time errors and provide better diagnostics and catch errors and portability problems. It was resource demanding, and this is why it did not become part of the compiler, but it was a separate tool. We use nowadays many such tools. Another idea, environment variables. Very simple, a syntax in the shell, key equals value, very small support in the kernel, and the C library that provides you with the get-env, the ability to get the value of a variable. These allow the easy configuration and the search for search paths, program behaviors. We use them for things today that were unimaginable in the past. Think of the keys that we code in environment variables and the API tokens. Another element was the documentation of the file system directory hierarchy. Again, convention over enforcement. Instead of providing a complex Baroque API of how to install the program, they said, this is where the program elements should be. Put them there, and your program will be universally available. Linux has also followed this and is documented. Importantly, the system was self-hosted, and this became a huge success. Here you see the rising number of commands through various versions of Unix. Again, on the 7th edition, write abstract programs that generate code instead of generating code by hand. With the 7th edition came language development tools, a lexical analyzer generator, LEX, and the grammar parser generator, YAC, yet another compiler. And amazingly, 12 programs were developed with these tools. This brought another idea to raise abstraction through domain-specific languages. So the system contained many what they called small languages at the time, from the shell and awk to the stream editor, the syntax of the find command, the exp command, the extended regular expressions of egrep, the M4 macroprocessor, and of course make that follows and dependencies and can work based on them. Not all lessons were completely positive. I also found one lesson that architectural innovations are sticky and face increasing resistance. This became apparent when Unix graduated from Bell Labs and went to Berkeley. There, they thought, okay, let's develop further libraries, and they developed some. They found that there were several implementations of regular expressions, each hosted in a different program. So awk had its own implementation of regular expressions, as had said, ed, grep, and exp. And they thought we can't stand for that, so created a regular expression library. But what we found, it had just one client, the more system similar to less, which was developed there. By 4.3 BSD, a later edition, several years later, it had two more clients, DBX and RDist. Interestingly, again, programs that were later developed. So once you get a decision, acquire some technical depth, such as creating 5 copies of the regular expression library, it seems to be difficult to pay it back. In FreeBSD, modern FreeBSD, I found that there are 4 replacements that are actually now using the library. Ed, grep, sed, and exp are now using the library rather than their own implementation. But it was painful. Another example, 4.3 BSD, 1991, offered stream I/O functions, similar to what GNU Fun Open Cookie added. This allows us to create a standard I/O stream and pass it on as a file, capital file pointer, and any function that uses standard I/O can access this stream through functions that we have created for reading and writing to it. This can be used to create layers of compression or encryption. But again, I've not seen a great uptake of this because it was developed quite late in the process. So we see that many core architecture decisions are taken at the beginning of the system's lifetime. And also these survive. So I've created a diagram here where each feature is seen as a line from the time it was born till the time it stopped to exist, from the 1970s until today. And you see that most of them lasted throughout the lifetime. So once you make a decision, once you offer a facility, this is likely to stay with you forever. So think carefully about it. Also, new architecture decisions are continuously made. The large Cambrian explosion that happened at the beginning hadn't stopped. You see here in yellow various others. But the rate of important architecture decisions declines over the system's lifetime. So we see that there are 39 the first decade and then 45 the next 4 decades. This is the result. That the result of this is that the system's overall architecture form remains the same. So here you may remember the architecture of the first research edition. Now, squint your eyes because I will show you the architecture of modern FreeBSD. Pay particular attention at the colors. This is the architecture. The system is not a few thousand lines, it's millions of lines of code, but has retained most of its architectural form, particularly in the areas that don't change. So the device drivers have changed completely because there has been a huge evolution of technology, but the top layers are very similar. The last lesson I think we can learn from the evolution of Unix is that package managers grow ecosystems and communities. Here I go to 386 BSD. A large part of the code that was developed at Berkeley was available to all thanks to the US government funding decision, which stipulated that code funded by the government should be openly available. And then a couple of people, Bill and Lynn Jolitz, when they saw this, they saw that most of Unix by the time was available as open source, and they just had to create a few missing files that were still copyrighted by AT&T to create a version of Unix that could run on Intel 386 architectures. They distributed it as a CD with the famous Dr. Dobbs journal. The uptake was huge, but unfortunately, they didn't continue to create further versions and take input from the community. So, a group of volunteers created what they called the 386 BSD patch kit, files that were patches containing metadata such as the title, author description, and the prerequisites for each part. And these organized community contributions converted 386 BSD from an open source software, which was at the time, to an open source project, a very important distinction. This was taken up with gusto by FreeBSD and other operating system distributions. One of the key and the only one innovation I will have time to describe here of FreeBSD was the production, the offering of a package manager, which offered the ability to patch the system, to compile the code, install it, uninstall it, and also, crucially, the handling of dependencies. Today, package ecosystems built around operating systems, repositories, tools, or even activities such as scientific computing are flourishing. They are enabling our community to build around open source software, and I think this is the most powerful lesson we can learn from the Unix operating system, to build communities around the technology. Thank you very much.